All right. Any questions about anything before we start talking about stuff? Questions? In case you haven't been, yeah. Oh, anytime, you know. Oh yeah, there's a box this year for 3250 homeworks up in the alleyway. You know, right where all the, like the 2200 homework box, everything. So just dump it in there and, you know. Any other, and if you want to submit it electronically, you can email it to me. You can email it a scan or a PDF or something, and I'll forward it to the people who are going to be grading it. Any other questions? So is everyone, is the career fair thing today and tomorrow or tomorrow and Thursday? Okay. Well, I have to announce that we have a special guest today who's recruiting for Cavium. Hi, Cameron. He took this class the last time we had video notes. So you know, we're doing it again this fall because I'm going to try to put in the wavelet stuff at long last and, you know, all that, whatever. But he works for Cavium, and he's sort of a hardcore computer architect nowadays. But he also does a lot of cryptography type stuff, and we just finished with that. We just finished like RSA and Hellman, Diffie-Merkle, all that stuff last week. So, yeah. Anyway, and he suffered through 3 classes with me over the course of his time at Cornell, which is one short of the record. So anyway, okay. And I think those guys who were you were, if you took 2200 last spring, you remember that we had guests from Applied Predictive Technologies. I think they're also here. Some of them are also here this week. So anyway, they'll be around. Anyway, okay. So we finished this sort of quote-unquote working with integers kind of stuff. And remember that I said that this is discrete, it's kind of clean, it's kind of neat to do, and you could see right away some applications. You don't have to worry about any kind of messy epsilons and deltas and continuity and all that stuff. Now we're going to start worrying about that kind of stuff, unfortunately. We have to bite the bullet. So the next sort of collection of topics is what I'll call working with real and complex numbers. And really, what I'm trying to do here, again, getting you used to some of the notation we'll be using throughout the semester, but also I'm trying to sort of set the stage for using this stuff to talk about systems, you know, linear time invariant systems and signals and all that sort of thing. And I'm trying to get everybody sort of on the same page, same initial conditions with this stuff. A lot of the material we're going to be talking about you have seen before, either in pre-calc or calculus or maths 1910 and 1920. And maybe you really learned it then, maybe you didn't really learn it then, whatever. And so some of the definitions are going to be familiar, and some of them I think will be new, I hope, so that it's not totally boring. Notation-wise, a lot of the results we're going to be talking about, so some stuff applies both to real and complex numbers, and some stuff applies only to real numbers. And I'll try to distinguish those cases. And the fact that some of the stuff applies to both real and complex numbers, to avoid saying real or complex every other word, I want to introduce a notation for real or complex numbers. So the notation we're going to be using is going to be this blackboard bold F. What does that mean? That just means, quote unquote, R or C, where that's the symbol we have for the real numbers and C is the symbol we have for the complex numbers. So results that apply to both the real and the complex numbers, I'm going to say for every thing in F, this holds. Okay? What do you think F stands for, anybody? Ricardo. What's that? Someone's grade. Your grade, or it's just someone's grade? Balage's grade? Okay, anybody else? Yeah. Varun. Yeah.
So if something holds for the complex set and the real set is a subset of all complex numbers, then isn't that
Yes, yes, we could just say for every complex number in this case. But I want to emphasize the separation between, for example, there's no such thing as a monotonic sequence of complex numbers, but there is of real numbers. So I want to distinguish things that hold for both from things that hold only for the reals. And you're right, what we could do is we could say the things that hold for both under the umbrella of for all complex numbers. We could do that. But that takes your attention away from the fact that it doesn't hold for the real numbers. So that's the only reason I'm using this notation. I apologize if it's cumbersome. Okay, but what do you think F stands for other than Ricardo's grade in the class? Field, yeah. Because remember, field is something where there's multiplicative inverses and additive inverses and commutative operations and all that stuff. Reals and complex numbers are fields. Okay, so a typical number in F is going to be like a subscripted Roman letter, like C0. So we're going to have things like C0 in F. That means C0 is a real or complex number. Okay, so the first thing I want to talk about is sequences. So here's some terminology, definition. A sequence in F, namely the real or complex numbers, is just a countable, one-sided countable set of numbers in that field. So it's going to be a set of numbers, and this is going to be indexed C0, C1, C2, and so on. So it's going to be an index sequence of numbers, and we could write it this way. The set of all C sub n such that little n is a natural number. That's another way of indicating that you've got this infinite sequence of numbers that are real or complex indexed by the natural numbers. Or, even more economically, and this is the notation I'm going to be using most of the time, Cn. So if you see this, what it generally means is an infinite sequence of numbers in F. Okay, so given a sequence C sub n, we say that it converges when there's some, say, C bar in F that the sequence approaches as n goes to infinity. And we have to make that notion of approaching precise. So colloquially, we say that the sequence, quote unquote, approaches as n goes to infinity, meaning that, and here I'm going to give you the classic definition: for every epsilon bigger than 0, there's some capital N in the natural numbers such that the distance between Cn and C bar is less than epsilon for all n bigger than or equal to capital N. Distance here, I'm using this notation, 2 vertical lines around the thing. If you're talking about real numbers, that means absolute value. If you're talking about complex numbers, that means magnitude. So note this means magnitude or absolute value, depending on whether you're talking about the complex numbers or the real numbers. So what this says is the sequence converges to C bar when, no matter how close you want to get to C bar, there is some point in the sequence after which every term in the sequence is that close to C bar. That's what it means for the sequence to converge to C bar. And math is full of these for every epsilon. There's an n and all that kind of stuff. And it's one of those opening lines that loses people instantly. Like, You could, I've said this before, some of you have probably heard me say this before, that, you know, there's those shirts that say you had me at whatever, hello world, you know, or hello or whatever. You lost me at for every epsilon bigger than 0 would be a good math t-shirt, because you definitely lose people when you start sentences that way. Anyway, in this case, we say that C bar is the limit of the sequence Cn, or we just say limit as n goes to infinity of Cn equals C bar. That's the math notation. All right, now you've all heard that before. You've all heard of what it means for a sequence to converge to some limit C bar. So I'm going to write up a couple sequences, and you tell me what they converge to. Or not, or tell me if they don't converge. So here's some examples. How about Cn equals 3 minus 7 over n squared, n plus 1 squared. Let's make it. Does that converge to anything as n goes to infinity? 3. How about this sequence? How about Cn equals 1, or let's write a few terms. C0 equals 1. C1 is equal to 1 plus 1 half. Well, let's do it this way. 1 minus 1 half. C2 is equal to 1 minus 1 half plus 1/3. C3 equals, and so on. You can see what I'm doing here. It's like an alternating harmonic series. Does anyone know what that converges to, or whether it converges? How many people think it converges? Okay, why do you, Aiden, why do you think it converges? He remembers that it equals something important, he just doesn't remember what it is. That's fair. That's totally fair. But do you have a better reason why you think it converges? You.
Just because, I mean, you're kind of pivoting around somewhere, and it's getting smaller and smaller, so it seems like it's going to go somewhere.
Yeah, Juice Young.
Kind of like Cauchy sequence.
We'll get there. We'll get to that in a sec. Cauchy sequence. Okay, let me recite this mantra that most people learned when they were in pre-calc. Every alternating series whose terms decrease in magnitude converges. Okay, we haven't even got to series yet, but anyway, it turns out that that converges. And it turns out that the limit as n goes to infinity, Cn is equal to the natural log of 2, but you're not supposed to know that. Okay, it is important, yes, fair enough. How about this one? C0 equals 1, C1 equals 1 point. Let's do a better one. C0 equals 3, C1 equals 3.1, C2 equals 3.14, C3 equals 3.1415, and so on. What does that converge to? Guess. Pi. Okay. How about Cn equals n? Does that sequence converge? No, doesn't converge. All right, so you all know about convergent sequences. So we can check that off. Now we get to Juice Young's question about Cauchy sequences. What is a Cauchy sequence? So here's a definition. Again, in this context, a sequence Cn in either the reals or the complexes is a Cauchy sequence when, and first I'll put the colloquial expression and then the rigorous mathematical definition. So it's a Cauchy sequence when, quote unquote, the terms in the sequence get closer and closer together as n goes to infinity. And we refer to these sequences when we're talking about where do the real numbers come from, that there are Cauchy sequences of rationals that don't have anywhere to go in the rationals. But here's the precise definition. What does this mean? I.e., For every epsilon bigger than 0, just like the definition of convergent, but a little bit different, there exists, so there's some capital N in the natural numbers, such that C sub m minus C sub n is less than epsilon when both m and n are bigger than or equal to capital N. That's what it means for a sequence to be Cauchy. Now notice that that definition doesn't tell you the sequence is going anywhere, like the definition of convergent sequence. It's going to somewhere, namely C bar. It says the terms in the sequence are getting closer and closer together. And wouldn't it be cool if whenever you had such a sequence whose terms were clustering closer and closer together, it went somewhere? Okay, so here's a fact. And I'll state it in two parts. A, if Cn converges, then Cn is a Cauchy sequence. And B is, if Cn is a Cauchy sequence, then Cn converges. And remember, we're talking here about sequences in the reals or the complexes. We're not talking about sequences of rational numbers or sequences of integers or anything like that. Okay, now it turns out we can prove part A in essentially one line, and I'm going to do that for you today. It turns out we cannot prove part B. Why can't we prove part B? We can't prove part B because in some sense we have stacked the deck. The real numbers are built, they're rigged so that part B holds, so that every Cauchy sequence has a limit. In fact, if you think back to the way we kind of quasi-constructed the real numbers, what we did was we added to the rationals limits to every Cauchy sequence. And it turns out when you do that, the resulting set you get satisfies that every Cauchy sequence converges to something. But the real numbers are rigged so that that holds. And I want to emphasize that. So it turns out we cannot prove, can't really prove B because essentially the real and complex numbers are quote unquote rigged so that B holds. Yeah, Ricardo.
So, I mean, like, basically, isn't it true by definition? What do you mean that, like, you can't prove it?
Well, when I say you can't prove it from first principles and definitions as far as I can tell. Okay, but if you think, see, there are ways of thinking of the real numbers. You can think of the real numbers as just being out there and you kind of discovered them under a rock one day and you're trying to figure out what's going on with them, right? Or you can think of it the way we thought of it using our revisionist history. Namely, you build up from integers to rational numbers, to real numbers, to complex numbers, and that method of constructing the real numbers gives you B. Okay, so in that sense we can prove it, but people who don't believe in that method of constructing the real numbers, which as I said is revisionist history, if they think of the real numbers as lying, say, under the cantilever part of Milstein Hall, and you just discovered them one day when you were walking up University Avenue, and you're figuring out what's going on with them, they can't prove B. Balazs?
Wait, so would a sequence that's the sums of the harmonic series, would that be a Cauchy sequence?
No. We'll get to series in a second. Okay.
Why would that not be a Cauchy sequence?
It isn't. It turns out you can prove it.
So they're not getting closer?
What's that?
They don't get closer and closer together?
No, they don't. Because you have to have, because if you say pin down a capital N, and we'll get to that in a few minutes, but if you pin down a capital N and you go out, any two indices beyond that capital N, the difference has to be less than epsilon. And if you go far enough out and add enough terms, you're gonna have arbitrarily big distances. So, and yeah, Nathan.
Is something like a sequence of square root of n fall into the same category, or would that be a Cauchy sequence?
The sequence Cn equals square root of n is just as bad as the sequence Cn equals n.
Don't they get closer together?
No, they don't. The adjacent term, I think you guys are both missing the same point. Adjacent terms get closer and closer together, yes, but this getting closer to closer together is a much stronger condition. It says that if I pin down a point in the sequence, or for every epsilon, I can pin down a point in the sequence after which any pair of terms is within epsilon of each other. And even though all the adjacent terms will be, separated pairs won't be. Okay? So that he had essentially the same question. Okay, but the point is you can't really prove B because the reals and complexes are rigged so that B holds. As for A, proving A is easy. And the argument I'm going to use is what's called an epsilon over 3 argument, even though we only use epsilon over 2 here. Okay? So, suppose Cn converges to C bar. Pick, given epsilon bigger than 0, you pick capital N in the natural numbers such that Cn minus C bar, magnitude or absolute value, is less than epsilon over 2 for every n bigger than or equal to capital N. And you can certainly do that. You can pick for delta being epsilon over 2 and n such that that works and just call delta equal to epsilon over 2. Then, for any m and n bigger than capital N, the difference between Cm and Cn, which is the same as the difference Cm minus C bar plus C bar minus Cn, by the triangle inequality is less than or equal to Cm minus C bar distance plus Cn minus C bar distance, which is less than epsilon over 2 plus epsilon over 2 equals epsilon. So the bottom line is, if the sequence converges to C bar, it's Cauchy because if you go far enough out in the sequence, here's C bar, all the terms are going to be within epsilon over 2 of C bar after capital N. And so any two of those inside this disk or sphere, whatever you want to call it, are going to be within epsilon of each other. And that's what it means for sequence to be Cauchy, that for every epsilon you can go far enough out in the sequence so any two terms past that point are within epsilon of each other. Okay. Bottom line, in the reals and complexes, convergent if and only if Cauchy. And that's another one of those things that you can write down on a little business card. People actually still write stuff down. I know they do. Oh, by the way, I have a question about idioms here. When you're talking about like using your phone, do you talk about doing stuff on your phone or in your phone? On, totally, right? Okay, you answered my question. I saw this video where this kid was talking about like doing stuff in your phone. Well, I know you're all probably doing something in your phone, in your phones. You know, you're doing something in your. And I'm like, wait, is this some kind of like Northwest U.S. idiom or something? Or, you know, I don't know. In Seattle, do they talk about doing stuff in your phone? Anybody from Seattle area? No? Okay. All right. All right, so you can put that in your phone, And so when you're doing stuff on your phone, you can be reminded of it, or you can write it down on a business side card, stick it in your wallet, and you're done. All right. So bottom line, in the reals or complexes, Cn is convergent if and only if it's Cauchy. All right. So we'll have a lot more to say about convergent sequences that you can spot easily in a little while. But first I want to talk about series. Promise we would talk about series. So here's another definition. If you're given a sequence that goes out like that, C1, C0, C1, C2, then we'll be considering, so the infinite series, and here we're talking about a one-sided infinite series. We will talk about two-sided ones in a moment. With nth term, Cn is the formal expression, and all this is chalk on a board for now. That's what it is. That's the infinite series. It's just that expression. But we have a way of reading that expression that gives us a hint as to what it's going to mean. Okay, I know I sound a little bit Dr. Evilish here, when I'm leading up to some of these results. But the way to read this is the sum from n equals 0 to infinity of Cn. Okay. How are we going to give it that interpretation? So, associated with this thing is a sequence, and we know all about sequences. And I'm going to call the nth term in this sequence S sub n. And S sub n is given by the actual number. S sub n equals the sum from m equals 0 to n of C sub m. And that's going to be true for all m n in the natural numbers. So if you give me n, I can calculate S sub n. It's a number. All I do is I sum all the terms in this infinite series whose indices are less than or equal to n. And that sequence, S sub n sequence, is called the sequence of partial sums of the series. So terminology. S sub n is the so-called nth partial sum of the series. It's not an abstract expression like the series. It's an actual number for each n. Since the SNs form a sequence, we can figure out whether that sequence converges or doesn't, whether it's a Cauchy sequence or not, all that kind of stuff. And when it does, we say the infinite series converges. So here's a definition. We say that the infinite series, and I'll leave out the word infinite, sum from n equals 0 to infinity, Cn, converges when the sequence of partial sums S sub n is a convergent sequence. And let's call the limit of that, in that case, S bar. And in this case, we call S bar the sum of the series, sum from n equals 0 to infinity of Cn, and we write this. We write sum from n equals 0 to infinity of Cn equals S bar. Now that expression, again, is chalk on a board. It's shorthand for saying limit as n goes to infinity, Sn equals S bar, where Sn is the nth partial sum of the Cn's. Okay, so we're trying to make this as orderly as possible. I'm trying to make it as orderly as possible. But, you know, you've seen all this stuff before, I'm sure, so far. Just getting you used to using certain notation and certain habits of thought, manners of speaking, whatever. Okay. So that's what it means for a series, infinite series to converge. The sequence of partial sums converges. Now I'm going to write down a few infinite series, and you're going to tell me whether they converge, and if so, what they converge to. Maybe. How about, so here's some examples. How about the sum from n equals 0 to infinity of, say, minus 17th to the n over n factorial? Does that converge? Okay, what does it converge to? Q sub. Something with E. Yes. For what it's worth, you are correct. Anybody know what with E? E to the minus 17th. Very good. This has a limit. This converges. And its sum is e to the minus 17th. Okay, how about this one? Sum from n equals 0 to infinity 1 over n plus 1. Does that converge? No. How come? Do you know why? You're right. It doesn't converge because, like everybody knows, the harmonic series diverges, right?
There's no minus component?
There's no minus component. Because not Cauchy. Yeah, that's a good new age use of the word. No. This series doesn't converge because pre-calc. Is that a correct use of because? Let me draw you a little picture, okay? Let me draw you a little picture. This is the graph of 1 over x. Okay? And now I'm going to put some squares here. Okay? So this is going to be 1, 2, 3, and so on. Okay? The area of each of these squares, or rectangles, is a term in that series. This is 1 times 1, right? This is 1 times 1/2, right? So the sum of the areas of these rectangles is bigger than or equal to the integral of this from 1 to infinity, right? So the sum of the series, sum of 1 over n plus 1, is bigger than or equal to integral from 1 to infinity of x dx, which is log x evaluated from 1 to infinity equals infinity. So that's the easy way to see why that series doesn't converge, okay? If someone comes up to you in Ho Plaza and says, does this series converge, and if not, why, don't tell them because pre-calc, okay? That's insulting. All right, so this doesn't converge. How about this one? Let's just change that one up a little bit. How about the sum from n equals 0 to infinity of 1 over n plus 1 squared? Does that converge? Yes? Why? Ricardo?
1 over n squared converges by the integral thing.
By the integral thing.
Yeah, it has a limit.
Not because pre-calc, but it has a limit, yeah. Does anyone know what it converges to? Does anyone know what the sum of that series is off the top of their head? I'll be impressed if you do. It's the natural log of e to whatever the limit is, yes. So in that sense, natural log is part of the answer. Anyway, it converges. And it turns out that the sum is pi squared over 6, amazingly enough. Not supposed to know that. So see, someone's going to look at their notes and they're going to say, why is the sum pi squared over 6? I didn't see how you got that, whatever. So I'm going to put down explicitly on the board, not supposed to know this. All right. Okay, so you've seen series before, you know, and there's rules about series, whatever, and so on. Okay. Here's a series that you encounter again and again and again throughout life, and certainly throughout this course. And we saw it a lot last spring, those of you who were in 2200, and we're going to see it a lot this semester. So I'm going to remind you of it. For those of you who didn't take 2200 or whatever. So here's a super important series. And here we have, you're given gamma in the complex numbers. And we're considering the infinite series sum from n equals 0 to infinity of gamma to the n. Does anyone know what that series is called? Geometric series. All right, so everybody kind of knows when that converges and when it doesn't, right? This board mechanism is getting more scary by the day. I don't know. When does that converge and when doesn't it converge? When does it converge? Varun. Yes. It converges when the magnitude of gamma is less than 1. And in that case, do you know what it converges to? 1 over what? 1 minus gamma, actually. Yeah. Okay, so let's prove that. So when does this converge? Here's a fact. This converges when the magnitude of gamma, remember gamma is a complex number, is less than 1, in which case the sum is 1 over 1 minus gamma. Let's show why that's the case. What we're going to do is get a formula for the nth partial sum. So we're going to let Sn, as always, be the sum from m equals 0 to n of gamma to the m, which is 1 plus gamma squared plus plus gamma to the n. Right? To show the series converges, we have to show that that sequence of partial sums has a limit s bar. It turns out it does when gamma is less than 1 in magnitude, and here's why. Note that if I take 1 minus gamma and multiply it by Sn, what happens? I get terms canceling out in pairs except for the 0th term and the nth plus 1 term. That's easy algebra. Thus, when gamma is not equal to 1, Sn is equal to 1 minus gamma to the n over 1 minus gamma. And I have to assume gamma is not equal to 1, else I wouldn't be able to divide by 1 minus gamma. And from that, it's pretty clear that when gamma is less than 1 in magnitude, that gamma to the n term goes to 0 as n goes to infinity, so S sub n itself converges, and it converges to 1 over 1 minus gamma. So since when gamma is less than 1, since the limit as n goes to infinity, gamma to the n plus 1 is equal to 0, limit as n goes to infinity of S sub n equals S bar equals 1 over 1 minus gamma, when gamma is less than 1. When gamma is bigger than 1 in magnitude, or even equal to 1, it turns out the series diverges. It doesn't converge. Okay, now this is another one of those, write it down on a card or put it in your phone so when you're on your phone you can read it. It's really important. Okay, now's a good time to take the 3-minute break, and then we'll talk about upper and lower bounds and ifs and soups and monotonic sequences and all that stuff. All right, so anyway, let's continue.
Yeah, so did I.
All right. Anyway, so we've talked so far about these one-sided series. I just want to mention that we will have occasion to consider two-sided infinite series as we go along. And let me talk about that for a second. So sometimes we'll encounter two-sided infinite series of the form sum from n equals minus infinity to infinity of Cn, where Cn is a real or complex number for all n. But now we're talking about n in the integers instead of n in just the natural numbers. What does it mean for a series like that to converge? So such a series converges when both the right-hand side of the series, the n bigger than or equal to 0 terms part, and the left-hand side of the series converges. So when both of these one-sided series converge, the right-hand side of the series, sum from n equals 0 to infinity of c sub n, and the sum from m equals 1 to infinity of c sub minus m, which is the same as the sum from n equals minus infinity to minus 1 of c sub plain old n. When those two one-sided series both converge, the two-sided series converges. And that's an if and only if. In some sense, it's the definition of what it means for a two-sided series to converge. It's not the same as saying so caution, this is not the same as saying that the limit as n goes to infinity of the sum from m equals minus n to positive n of c sub m exists. So you can't sort of let both sides of the series go out to infinity and say if that sequence of numbers converges, then the two-sided infinite series converges, because that allows for perverse things to happen. Okay, yeah.
So I think you just answered my question, but stuff like limit from n minus infinity to infinity of n.
Exactly. That's the perfect example. Yeah. Like, for example, if I write this thing, the sum from n equals minus infinity to infinity of n, that thing does exist. That limit does exist, but that doesn't converge by our definition of convergence, even though that thing works. Excellent example. All right, so we're going to see two-sided series as we go along, and especially when we're talking about, say, summable signals and z-transforms and all that, we'll see those quite a bit. Okay, so now I want to talk for a little bit about upper and lower bounds, ifs and soups and all that, and now we're going to have to focus on real numbers only for a little bit. Okay, so next, what we're going to do is talk about upper and lower bounds, etc., for sets of real numbers. Okay. And this is really important. You all have kind of an intuitive grasp of it. But let me try to sell you on why it's good to study this carefully. Whenever you're trying to solve engineering problems, you're always trying to, maximize something or minimize something. You're trying to maximize throughput, minimize cost, minimize latency. Maximizing and minimizing things is really important, subject to some constraints. Like you may have a constraint on your resources, or you may have a constraint on how many people you can assign to the design project or whatever. These things involve constrained optimization problems, and all those problems take the form of maximizing and minimizing things, finding upper and lower bounds, finding the theoretical best you can do and seeing how close you can get to that. That's where bounds come into your life, okay, on a regular basis. So here's a definition. A set A of real numbers, so A is a subset of the reals, is, it's going to be a three-part definition, bounded from above if there exists some let's call it V upper bar in the reals, such that, and what do I want to use for an, let's just use V's and stuff, so that A is less than or equal to V upper bar for all A in capital A. And it's bounded from below when there exists a V underbar in the real such that A is bigger than or equal to V underbar for all A in capital A. And it's bounded, just plain old bounded, if what? What's a cool way of saying bounded now that we know what bounded from above means and bounded from below means? It's both bounded from above and bounded from below. Okay, so that's what it means for a set to be bounded from above, bounded from below, or bounded. And you all intuitively know what it means for a set to be bounded from above. Like if you drew a number line, the reals, and you drew your set A, then there'd be some point to the right of A, right? That's bounded from above. Some point to the left of A, bounded from below. A point to the right of A and a point to the left of A, so A is contained in some bounded interval, that's bounded. All right? Now, in this case, we call V upper bar an upper bound for A, and V lower bar a lower bound for A. So V bar in the definition is an upper bound for A, and V underbar is a lower bound for A. Okay, so I'm going to give you a bounded set. So for example, A equals the set of all x's in the, or A in the reals such that minus pi is less than A is less or equal to pi. Give me 3 different upper bounds for A. 3 different upper bounds. 10. So upper bounds. 10, give me 2 more. Pi. How about another one?
420.
420? 420. Did I just hear 420, or was it supposed to be 4 to the 20th? Like, I was going to propose 10 to the 59th. You know, that's a perfectly good upper bound for A. If you want to be sure, okay, what are some lower bounds? Minus 10 to the 59th, minus pi, and minus 420. Excellent. Okay. All right. And 10 to the minus 59th is also a lower bound, too. Okay. Now, clearly, there's a variety of upper bounds for any bounded from above set, a variety of lower bounds for any bounded from below set. And some of them are tighter than others. Like, I challenge you to get better than pi as an upper bound or better than minus pi as a lower bound for that set. Anybody think they can do that? He or she can do that? How many? Okay, we're not running a finite precision course here. Okay. But, you know, if someone comes to me and says, you know, we know that eventually you're going to get a throughput or latency between minus pi and pi. That's a tight kind of thing, rather than saying, well, you know, your latency could be as long as 10 to the 59th years or as short as 10 to the minus 59th seconds. You know, that doesn't help you very much, right, when you're trying to solve a real problem in real life. So in some sense, the moral of this little tale here is some upper bounds are better than others, some lower bounds are better than others, and when I say better, I know that's a value-laden term, but what I'm talking about there is in some sense tighter. So here's a fact about real numbers, a cool fact. So here's a fact. If A is a subset of real numbers, then if A is bounded from above, then A has a what people call a least upper bound. And I'm not fond of that terminology for stupid linguistic reasons that I'll explain to you in a second. V double bar, I'll call it. What does a least upper bound mean? That is to say, V double bar is an upper bound for A and every other upper bound for A is at least as big as V double bar. And similarly, you can go through the same drill with below. So if A is bounded from below, then A has what's called a greatest lower bound, and I'm going to call it V double underbar. That is to say, V underbar is a lower bound for A, and every other lower bound for A is less than or equal to V double underbar. Now, the stupid linguistic reason I don't like this terminology is least upper bound. To me, that sounds like the upper bound that is the most unupper of all upper bounds, rather than the lowest upper bound. I'd rather have them say lowest upper bound. Greatest lower bound sounds like the absolutely epically coolest of all lower bounds, rather than the highest lower bound. So that's what I wish they would say. I know that that's pedantic and all, but anyway, this is the terminology we've settled on. Notation is V upper bar, double bar, the least upper bound of A, is the sup of the set A. And the greatest lower bound is called the inf of the set A. And those notations, that's leftover, Latin stuff. Sup is short for supremum, and inf is short for infimum. You don't have to know that. You just have to know infant soup. Erica.
What's the point of defining a bound if there's bounds that go above it, or what's the point of having an upper bound if there's upper bounds that and lower bound?
Okay, your question is, roughly speaking, why should we care about any bound for a bounded set other than its least upper bound and its greatest lower bound? Why do we even care about 10 to the 59th here? Well, it turns out it's sometimes it's hard to figure out the greatest lower bound or the least upper bound of a set. But it's good to know that they're there when they are. Okay? Sometimes we can only get a rough guess of it. And lots of, like for example, in information theory, you have to figure out how fast you can pump bits through a communication channel, you know, how many bits per channel use, how many bits per second. There's something called the channel capacity. And trying to achieve that, and you know, you're always coming close but not quite as close. You know you can get, you know that there's a certain number you can hit, but you can never hit it with all the things you're doing. And so a lot of your, like, deciding whether the scheme you come up with is good is bounding from above how, I don't know. I'm not giving you a good answer, I don't think. Yeah?
Is a good analogy to it, like, we know that there is absolute zero Kelvin, but what humans can survive to is way above that, but it's a lower bound too.
If that works for you, yeah. She's, you know, Kelvin, humans can only survive to whatever, minus 40 Celsius. No, actually, minus 40 Fahrenheit.
It's just finding the smallest space that you can pack a couple bytes and set it to, right? That's what we're-
Finding the smallest space you can pack a set into, yeah, essentially, yeah. Smallest interval, yeah. But anyway, the thing is, it turns out that every set of real numbers that's bounded from above has a least upper bound. Every set of real numbers that's bounded from below has a lowest upper bound. So every set that's bounded has both a least upper bound and a greatest lower bound. And do you think we can prove this fact? Well, it turns out that you can't prove this for the same reason you can't prove that every Cauchy sequence of real numbers has a limit. Real numbers are rigged so that this holds. Okay, so it turns out that you can't prove this because R is rigged so it holds. However, of interest, at least to me, is that it's equivalent to the other rigged thing. So it's equivalent to, quote unquote, every Cauchy sequence converges. What do I mean by equivalent? I mean that you can start with the assertion that every Cauchy sequence converges and prove the upper bound, lower bound property, or you can start with that property and prove that every Cauchy sequence converges. But those properties are out there floating in the universe on feet of clay. You know, there's no way to prove either of them from lower down principles. And actually, if you look in the monograph, I give you a proof that those two properties are equivalent. Okay? So that's what upper bounds and lower bounds are. And soups and infs. Let's look at a few examples of sets of real numbers. So here's some examples. First one was A equals, let's just do the pi one again, the set of all A's such that minus pi is less than A is less than or equal to pi. That one we already discovered was bounded from above and below. What is the sup of A? You could just shout out the answer. Pi. What's the inf of A? Negative pi. How about this one? A is the set of all things of the form. Well, let's make a finite set. How about 1, 3, or let's do an interesting one. 2, 3, 5, 7, 11, 13, 17. What is the sup of A? Say it louder. 17. What's the nth? Okay, how about this one? A equals the set of all e to the minus n such that n is in the natural numbers. What is the sup of A? And what is the inf of A? Which sup of A is, someone said 1? Is that right? What about, what happens when I put n equals 0 in there? 1. And if I put any positive n in there, I get something less than 1, right? So the sup of A is 1. What's the inf of A? 0. Yeah. Everything in there is bigger than 0, but I challenge you to find anything bigger than 0 that's still a lower bound for A. The greatest lower bound, the tightest lower bound you can get for A is 0. So those are just some examples of infs and sups. How about this one? A equals the union of two intervals. How about the interval minus pi to minus 1 union with the interval 1 to 10 to the 59th? Open interval. What is the sup of A? Say it louder. Yeah, 10 to the 59th. What is the inf of A? Okay, so you know, you understand all this stuff really well. Infs and sups and everything. Sups are kind of like maxes. Infs are kind of like mins. How do we make that precise? So here's definition. If you're given a set of real numbers, so if A is a subset of the real numbers, then what is true? If there's some A, call it A bar in A, such that A is less or equal to A bar for all A in A, we call A bar equal to the max of A. And on the other hand, if there's some A underbar in A such that A is bigger than or equal to A underbar for all A in A, we call A underbar the min of A. Now, the min of A and the max of A don't always exist. Not every A, not every capital A, even the ones that are bounded from above, have maxes. And not every bounded from below capital A has a min. So here's a caution. So not every A bounded from above has a max, and not every A bounded from below has a min. And let's look at our examples up there. Unfortunately, they've taken away the 1960s. Oh, no, here it is. Yeah. Manish?
So the only difference between a max and a soup is that for a max it has to be actually present within A.
Yes, and that's going to be the theorem that we close with today, maybe, or open with next time. Like, here's the 1960s laser pointer again. Does this set have a max? This one here? Does it have a min? Does this have a max or a min? Yes. Does that have a max?
Yes.
Does it have a min? Does this have a max? No. This, remember, A is this whole set, this union of two intervals. Okay. Does it have a min? Okay, you get it. Fact. Manish's theorem. And then we'll open with this next time. I'll like to get your question in a second. That if A is bounded from above, it has a max if and only if its soup is actually in the set, in which case the soup is that max. It has a min if and only if its inf is in that set, and in that case the min is the inf. Yes, question?
If you have like negative n in parentheses, then you raise that to the n power. So like for example, like -1 and then 4 and then -9. And
Yeah.
Well then, how do you make a upper bound and a lower bound for that?
That set is not bounded either above or below.
Oh, that's just it.
Yeah, yeah.
Okay.
Okay.